often quoted anecdotes really had a profound influence on my scientific career. They are, if you're knowledgeable, if you're not knowledgeable, you're in darkness. And if you're knowledgeable and don't share your knowledge, you will fall into more darkness. That is one. The second one he always tells us is, whatever you do in science, if you can't realize it to nature and you can't explain to your grandmother what it is about, it is a waste. And let's all come out of that darkness by listening to his illustrious lecture. Ladies and gentlemen, once again, welcome Dr. V.P. Rao.
Thank you, Professor Ramakrishna. Very nice to see you all. Good afternoon to everybody. First of all, I will quote something from what was called Taitra Upanishad. You all know what is Upanishad? Maybe you all know. Upanishads are at the end of the Vedas. So they are called Veda Anta, end of the Veda. And one of those is what's called Taitra Upanishad. In that, there is a sloka, which sloka you all understand. That's something like a poem. And in that sloka, it is a dialogue between teacher and the taught. So very relevant to today's and another two more lectures. And the sloka is Om Sahana Bhavatu Sahanau Bhunaktu Sahaviryam Karavavahai Tejasvi Navadhitamastu Ma Vidvishavahai. What it means is, Om, you all know, the cosmic sound of Sahana Bhavatu. May he give us energy. Sahana Bhavatu, Sahanau Bhunaktu. Bhunaktu means not just eating. Just eating is eating. Bhunaktu means may he give us nourishment. Eating is different from nourishment. All that you eat will not go for nourishment. Only some of it goes for nourishment. So may he give us nourishment. Sahana Bhunaktu Sahaviryam Karavavahai. Let all this about the supernatural God or the teacher of everybody. Teacher of everybody. So may he give us energy. The most important thing, which is in the emblem of Andhra University, Tejasvi Navadhitamattu. What it means is, let our education be effective and vigorous. Effective and vigorous. Whatever you do effectively and vigorously. And I add myself one more thing, meaningful. So your study should be effective, vigorous, meaningful. And finally, Tejasvi Navadhitamastu Ma Vidvishavahai. Let there be no evil thoughts. Ma Vidvishavahai. Om Shanti Shanti Shanti. Let peace prevail everywhere. So this is actually a dialogue between teacher and the taught. One of the things I believe very much is, whatever the student learns, you should learn from, I believe, from Guru Mukhataha. The Guru should teach, is it not? So anyway, today we'll start one of the first papers of modern meteorology. The groundbreaking discovery of what are called now Rossby whale by Professor Carl Gustav Rossby in 1939. Even I was not born. I was born in 41. So that is almost 80th year old. Unfortunately, I'm sorry, maybe none of you read that paper. Anybody read that paper? So one of the groundbreaking discoveries of what are the Rossby whales, which are the basis of modern, let us say, theoretical meteorology. So today I will give a little bit explanation about this original paper, and there are some very, very important features about this paper. And Professor Rosby, he was in the so-called veteran school in the Scandinavian countries, Norway, or I think Norway probably. And there they were, you may be knowing some of you, there is something board at a glass, and underneath the light, they keep a chart. We used to do in Andhra like that in 60s. And chart we used to draw isobars, those things. They used to do this. Professor Rosby and many colleagues there in Belgian board. So, when I was here in ITM, at the time it's called ITM. It was a part of Government of India. And then later it became IITM. When I was in India, IITM, when Professor Murakami came, he was here for 1 year. He taught us how to go about, let us say, theoretical meteorology, which I think is very important, which forms the basis of all the modern meteorology. Theoretical meteorology is something like this. Suppose you have a concrete pillar, on above that the whole apartment, all those things. In the concrete pillar, you have stone, cement. But what is important is the iron inside, which keeps it firm. That iron inside, for us, is theoretical meteorology. More mathematical, more rigorous, solid, I should say that. So, this paper 1939 is one of those papers, which actually gave the solid base for the modern theoretical meteorology. And this was in 1939. So, because of his experience with the observations, and so the idea was he was fitting a theory to what he was observing in the what to call those latitudes, the higher latitudes, middle and high latitudes. And also, please pay attention, in most of the research, theoretical research, whether it is physics, meteorology, or anything, normally they fit theory to observations, But in our case, meteorology, there is one paper where theory preceded observation. That was by Taro Matsuno in 1966, Journal of Meteorological Society of Japan. He discovered, that is the correct word, because I think this 1966 Japanese paper is as important as the discovery of the Rossby waves in 39. And in this paper, he got a solution, mathematical solution, published in 1966. First, he got a solution. Maybe you all heard now what are called equatorially trapped waves, Kelvin waves, and mixed Rossby gravity waves. You all know, you all must have heard, but I doubt very much the real theory behind it. Anyway, I derived the whole thing step by step with Matsuno's paper. In the Matsuno's paper, it is highly theoretical. He solves what is called Schrodinger equation. And I myself had to learn first mathematics. I bought a book, Mathus and Walker, Theoretical Physics and Applied Mathematics. I myself derived some of those solutions, then got to this. It took about 6 months to me to understand the mathematics behind it. Of course, theory or meteorology. So in that, he discovered first these waves mathematically, then everybody went to see them in the nature. And the so-called Kelvin waves, Kelvin waves are actually gravity waves. And then mixed Rossby gravity wave. This particular wave behaves like for the higher wavelength as Kelvin wave, for the lower wavelength as the Rossby wave, which has mixed characteristics. These two types of waves are trapped near the equator. trapped near the equator. And the amplitude decreases exponentially towards higher latitudes. So the amplitude e to the power of minus y square by 2 or something like that decreases rapidly towards higher latitude. So these are actually what are called equatorially trapped waves. So, and these are, he discovered theoretically, then later, Maruyama and Yanai, they discovered the mixed Rossby gravity wave and the Kelvin wave were discovered in the atmosphere by Wallace and Kowski. So what I am saying is, mostly in our science, atmospheric and oceanic sciences, first we see observationally, fit a theory to it. Only this is the only exception. So what I am saying is, what I am stressing is, Professor Rosby, he saw these waves in nature and he fit a theory for it, for these waves. Now, there are certain features for this particular analysis, theoretical analysis of Rosby. Normally, we have U equation and V equation. The vector wind has two components, zonal and the meridional. So if you treat wind, you have to treat two equations, two different equations. Rosby said, no, I treat only one. I want to treat only one. So he had the perception already those days because he was working with observation. Because he was working with observation, he had very good knowledge. There's something extraordinary with him, with Professor Charney, with Professor Phillips, some of those forefathers who have built a theory for the modern meteorology. They have very good perception of the real nature. That's how they could fit. And very another important aspect. Normally, unlike the theoretical physics, where they are interested in complete mathematical solution. In our case, the case of atmosphere and oceanic sciences, our purpose in the case of meteorology is to predict. So, just like in the Rosby paper 1939, he has a good idea of what he has to find out or discover. So, the mathematics is not that rigorous. The case of theoretical physics, the correct word is the mathematics is very rigorous. In this case, his purpose was not the rigor of the mathematics, but he wants a theory because, please pay attention, you all students, if you don't have theory, for example, I say temperature increase. Temperature may increase 2 degrees or 100 degrees. So that gives the quantitative knowledge. So the equations, theory gives the quantitative knowledge, not qualitative like synoptic meteorology. So that is the purpose of theoretical meteorology, to keep bounds to your thinking, to keep bounds to your analysis. And once you have a solution, it is, suppose for example, sin x between 30, 40, you know what it is. So if you just say it is a wave, it is not, we don't have bounds. So in this case, and also one thing very important is, there are two types of solutions. Anyway, later I will talk more about this. And now, he wanted to solve only one equation. I don't want to solve two equations. So what he did, what are the equivalent of U and V equation? What are the equivalent? What are the equivalent equations? Vorticity and divergence equation. Vorticity and divergence equations are equivalent. And pay attention. He has already perception. In the case of at least middle and high latitudes, the ratio of divergence to vorticity is all the order of the Rossby number 1/10. That is, in other words, divergence is about one order of magnitude. And also pay attention. There is what's called scale analysis. Scale analysis is similar to dimensional analysis, but in the case of meteorology, who introduced some of these forefathers like Crosby. There is another fantastic professor at MIT, Jules Gregory Charney. He developed what's called scale analysis. You already must have heard the scale analysis approach. It is like dimensional analysis, and pattern, it is semi-quantitative. See, mathematics is quantitative, but this particular scale analysis is semi-quantitative. The idea is, suppose you say U is the order of the magnitude, not equal. U not identically. It is about the order of 10 meters per second. So this particular type of a novel, again, innovation, and also for all of you, patent, all of you researchers, the catch word, please, catch word is innovation. You should discover something, you should try for it. Even if you don't get, try for it. The catchword is innovation. So Crosby Wills is one innovation. Then Charlie's scale analysis, another innovation. Then Charlie's quasi-geostrophic theory. Quasi-geostrophic theory is another innovation. Berkeley instability is another innovation. Arakawa. So these are some of the what you call forefathers of modern theoretical meteorology. So whatever you do, whether it is observation or theory, you should have quantitative ideas. Suppose say temperature increase. Temperature can increase 1 degree or 100 degree. You should have the number or the theory and this theoretical equation that these equations put bounds on these numbers. Anyway, so he said, I want for only one equation. So he already had, from observation, this perception that divergence is an order of magnitude less than the vorticity. That's just the middle and highlight. So divergence by vorticity is the order of Crosby number. So instead of treating two equations, U and V, he treated just one equation. What's the equation? See, that is the brilliance, that is the innovation. You see, these are some of the things very important. Now, he already had a good idea about what are Rossby waves. What are Rossby waves? Rossby waves are rotational waves. They are generated by the Earth's rotation or any rotating body. Wherever there is rotating body with fluid inside or outside that generates Rossby waves. So there are Rossby waves in all rotating planets. That's why there is, I have again derived completely. These are available. I can give you my notes. And Professor Charney, he has a book, not a book exactly, a treatise of a derivation, planetary fluid dynamics. See, pay attention to the title. Although it is applicable, it is applied to meteorology, but the theory is for all planets, all mostly rotating planets, planetary fluid dynamics. So the approach is hardcore theory, planetary fluid dynamics. I have completely derived the whole equation. Anybody you can have, it's not easy. It's quite complicated. You have to sit on that turtle and in any case. So he has taken only one equation, the vorticity equation. And also, again, as I put in the title, please pay attention. There are mainly two types of waves in the atmosphere or in the ocean. Because most of our study, at least the theoretical study, all the theories are applicable to atmosphere and ocean. And in fact, this particular paper, which Rosby 1939 discovery of Vivel, was published in Journal of Marine Research, in a oceanographic journal. Although it's applicable to atmosphere and ocean, see, fluid. That's why the Charles analysis is planetary fluid dynamics. Planetary fluid dynamics. Anyway, this Rosby now, he uses only one equation. What's the equation? And again, now he says, I don't want to complicate spherical geometry, because you have to then embark on spherical harmonic, Legendre polynomial, those things. No, I don't want to do. So I want to do only Cartesian geometry. I want to use only Cartesian geometry. So what he did, pay attention. Again, one more innovation. See what he calls as beta plane. So beta plane, what is beta plane? I think you all got a paper, one of my very early papers, 1969, pure and you all got?
No, I have posted it to Vinu, sir.
Huh?
Vinu, he has shared.
Yes, you all received, I think. In that I derived because, pay attention again, beta plane approximation. Beta plane approximation. When you use the word approximation means there are errors in that. There are limits to applicability. It's applicable only to certain things. So beta plane approximation, just like hydrostatic approximation, geostrophic approximation, any type of approximation has limits. Obviously, you all know that, is it not? Like that, he doesn't want to use, he did not want to use spherical harmonic or Legendre polynomial to complicate. So his purpose, he knows where you want to reach. That's something very, very important. Please, Patrick, you are all research students. You should know where you want to reach. And for that, he doesn't want to complicate. And only simple theory, but with the purpose of having solid knowledge or so-called Rosby waves. As I put in my title, his analysis is Rosby wave, neutral waves. Why neutral? Because in the case of atmosphere, we all know, but there is very innocent small depression, very, very small low, very small, innocent, and then slowly it grows. Slowly it grows. So it's wave like that, then it grows like that, then it grows like that. For mathematically, amplitude grows. Mathematically, amplitude grows. Growing of amplitude of the so-called Rosby waves, the wave should be unstable. Or if the amplitude grows, for example, V amplitude, median, if the amplitude grows, V square by 2 grows, or kinetic energy is growing. If the kinetic energy is growing, total energy, conservation of energy, constant. Is it not? It's coming from something else. Or, pay attention again, which I will treat later on. I don't need, if time permits. So, these waves, which are growing, are called unstable waves. There are 3 types. Stable means d by dt of k less than 0, or kinetic energy decreasing. Kinetic energy decreasing with time is called stable. Kinetic energy increasing with time is called unstable. And kinetic energy equals to 0, neutral. So, in the original this Rossby theory, there is no energy source from which the disturbances can, what you call, take the energy. Because the disturbance have no source of energy from which they can extract energy. These waves are neutral waves. That's why I put the title neutral. The original Rossby theory is a neutral wave theory. Okay? Neutral wave theory. So he uses only one equation, beta plane approximate, not the sphere, and also u, the zonal wind. You know the nonlinear from u d by dx of u? U d by dx of u is linear or non-linear? Non-linear. Why? Because the independent variables x, y, z, t, 4, and dependent variables u, v, t, specificability like that. And then u du by dx is not is d by dx of u square by 2. Okay? U du by dx is d by dx of u square by 2. If you plot a curve with the independent variable x and dependent variable u, it varies quadratic, not linear. Quadratic, linear is u only, is it not? But it is u square. So, if the coefficient of the term is a function of the dependent variable, then it is non-linear. Okay? So simple to explain. Non-linear means the variation is not linear. So he says, no, I didn't want to solve non-linear terms. I want to solve only linear terms. So what he did? So that u, v, all those things, he simply took zonal average. And his zonal wind u bar is independent of y, independent of p, independent of x. It's a constant. So, because, pay attention please, because the zonal wind is constant, there is no energy from which the disturbance can extract. That's why the disturbance are neutral. So, if you have a model where the meridional variation of u exists or the vertical variation of u exists, if it is the vertical variation, then we say it is baroclinic instability. If it is meridional variation, we call it barotropic instability. Instability means the wave can extract energy from the mean motion. But the original Rossby wave is neutral. There is no energy source in it. There was an energy source. That's why I have put the title neutral waves.
Next slide, Betlem.
Huh?
Next slide, Betlem.
Better to which end? So anyway, if you are going to the heart of the Rossby wave, I want to show you the figures of some of the very, very famous meteorologists. The first, this side, left side top is Professor Rossby, and right side is S. Manabi. You all know the Nobel laureate, Nobel Prize winner of 2021 in physics. So now you all have a tremendous boost that even meteorology can give a Nobel Prize. See? And then this is that famous Edward and Lawrence. You all know his name, Lawrence, must be knowing all you, is it not? Lawrence theory, another great name. And this is Paul Crutzen. Paul Crutzen, the Nobel Prize winner of chemistry, is it not? Actually, his PhD was in meteorology. So he was the first by definition, meteorology to get an old price. Although for chemistry. Then again, this is for chemistry, that is for physics. Okay. Next matters చూద్దాం. పుట్టిన దించండి కొన్ని పైనుంచి. Let us read. Anyway, here Paul Cutzon's views. You all can read. You all can read everywhere. He is a strong believer in the fact that contributions from individual scientists are essential for the progress of science. Normally, these innovations, not in group, people do innovation individually only. You only individually get ideas. Not in a group, you don't get it. It's not. So, another, he has some misgivings about the high degree of direction that atmospheric chemistry is experienced today. That is, in his view, increasing bureaucracy and war organization. Some of things are very important, not too much on the limited personal resources in our field and hamper, not hamper original research. He senses a loss of proper balance between more individualistic basic research and large-scale applied motion. The less bureaucracy, the better. One of his, this is important, please. Please read this. One of his beliefs is that a journal like ours must allow the publication. He founded what is called atmospheric chemistry. He founded a journal called Atmospheric Chemistry. In that, this is published, that atmospheric chemistry. He says, see, the most important, see, this is very, very important to all of you. Pay attention, please. You see, one of his beliefs is that a journal like ours must allow the publications of paper which are off the beaten track. Means, you see, there are two types of. Suppose you have no road. So, somebody builds the road, with a lot of effort, then everybody goes on that. So, the first person who builds the road is the key man. So, what he says is, don't go on the beaten track, on the road already built. Try to go other sides. So, this is important for you all who are doing PhD. How to go about the research, the basic research, what you call the innovative research, which I was talking about. So here it says, one, you should go off the beaten track and contradict the current views. And as long as the authors provide plausible arguments for their position, the risk, read this, the risk that such a paper may turn out to be wrong. Okay, it can become wrong. Or in other words, suppose there is a road. On the road, if you go, it's okay, smooth sail, smooth sail. Suppose you go on the other side. You may go, reach something, end of the road. There's no, then you have to come back, is it not? So what he says, the risk that such a paper may turn out to be wrong will be overcompensated by the fact that the ensuing controversy will simulate scientific progress. That is, you don't go on the beaten track, or in other words, don't go along the already known theories, the known views. Go something very different, and you go on that, you may end up end of the block, or the one you are thinking may be wrong, it may prove wrong, but it doesn't matter. That's what he says. Actually, as you go on that, publish in a paper, then there will be a lot of controversy. Hear me this. There is a Charles Darwin quotation. Here. False views. Hear me please. False views do little harm for the progress of science, because everybody takes a salutary pleasure in proving their falseness. Or in other words, suppose you say Pune is very, very cheap, for example. Then say, no, 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 no. The first idea is to contradict. So, in this science, normally the tendency is to contradict. So, even if you give a false idea, for example, Pune is very, very cheap, and we know it's not, very expensive. Then everybody, no, no, it's not cheap, it's expensive. So, it doesn't matter. So, if you give a false view, everybody takes a salutary pleasure in proving their falseness. These ideas fall. On the other hand, false data. I remember when I was in the university 1960, in the university also, some of our students were employed in India Meteorology Department. And they were assistants just doing MSc. They have to take the what you call the radars on day Ravin data, radars on day pilot balloon data. And some of the friends used to put a take their temperature and all. Same thing, they put +1, -1, -2 for the next day, and another -1, -2 for the due day. And you people take the data as something authentic. Is it not? You just to put, if they don't want to go, take leisurely, put +1, +2, +0.5. This is exactly what he's saying, Charles Darwin. False data do a great harm for the progress of science. Is it not? So this is the false data. Is it not? I gave a good example. It happened. I know some of my classmates who are launching this. Okay, it's okay. They take the yesterday data plus 0.5, 0.2, like that, just put it. And some of them, maybe another fellow put 0.10 or 0.1. Then we think, what is this? Something very, very different. And if they try to take the data, explain it, it's all false. Is it not? So that's exactly what he said. False data do great harm because it endures long time. False view, Pune is very cheap. That type of thing, nobody accepts. Then immediately it's corrected. Immediately, that is the idea. So anyway, now we come to the original. That is the title, and it's published in Journal of Marine Research. I already explained some of the basic features of this paper. He takes what's called neutral wave because there is no energy by which the waves can grow, and also once you take, again patterns, like the approximation, any type of approximation has limits. You should know that. So if you take neutral wave, what it cannot explain. That's why I have put the next lecture, why you have to embark on instability theory. What the neutral theory cannot explain, and why we should go for a complicated instability theory. Anyway, now he uses what's called the beta plane. What is beta plane? Again, pay attention. Imagine a cylinder. Imagine a cylinder. In the cylinder, there is a sphere such that the radius of this sphere at the center touches the cylinder. I repeat, there is a cylinder, there is a sphere, and the radius, rather diameter, at the equator touches the cylinder. You do not, you can imagine easily that. Now, nobody's sleeping, is not. Sorry. Anyway, so you will sleep, wake up. Now imagine the cylinder is like this. Increase. Go on, increase. Isn't it? The cylinder, if you increase the radius or diameter, slowly, is it not? What is this? From the cylinder at R infinity, what it becomes? Plane. Is it not? If you increase the surface at infinity is a plane. So this is beta plane. So if the earth sphere touches at the radius, at the equator, and then there is, if you imagine a plane that is touching the diameter, is it not? And the radius is so large, or the diameter is so large, is it not? It is almost like a plane. So this is the beta plane. But again, pay attention. This is equatorial beta plane because it touches at the equator. Equatorial beta plane. And the equatorial beta plane, you all got Raspberry paper? Pumbistara, Abhay? He will send that.
Yeah.
So, and then now again, beta plane approximation. So there is a limit, the validity, when it is valid, when it is not valid. I wrote a paper in 1969, a first paper in 69. I have some elementary analysis in that. Take a look at that. When it is valid, when it's not valid. Again, remember, any type of approximation, beta approximation, adiabatic approximation, quasi-geometric approximation, any type of approximation has a validity, isn't it? So, if you write the Coriolis parameter, F equals to, you all know what is Taylor series? Do not. So, F equals to F0, df by dy into dy, plus 1 by 2 factorial d square f by dy square into dy square, series. It's a series. And now, if you take only the first two terms are linear. Why linear? Because f is equal to f0 plus beta y. Next term is y square. Is it not? So first two terms are linear terms. So if you take f is equal to f0 plus df by dy is beta. So f0 plus beta y, leave every term. So f is equal to f0 plus beta y. F0 is a constant, beta is a constant, and it varies linearly with y. And if, as I said, if it touches the equator, it's called equatorial beta plane. F0 at the equator, how much is it? 0. So F0 equals to, F is equals to beta y, 0, 0. Beta y is equal to the beta plane. Okay? Same thing, if you imagine something similar like this at 45 degrees north, then it is something, it's called middle latitude beta plane. Again, don't forget, middle equatorial beta plane, approximation. Middle latitude beta plane, approximation. Hydrostatic, approximation. Geostrophic, approximation. Quasi-geostrophic, approximation. So there are limits to this. There are limits to validity of this. When the beta plane is valid. In the original Raspberry paper, probably you all get that. The original paper,
yeah, at the end of the lecture,
we requested the man to send all of you these two papers. So, in that, to defend his argument, let's put a table. Put the value of beta. It says almost constant. Let's calculate how much percentage it varies. To defend beta is a constant. Okay?
next slide.
Next. Oh, anyway. Now, hear me. And normally, suppose you have an equation. What's the equation? You all say dou or d. This is a partial derivative. I continue saying d only. d zeta by dt plus equals to u d by dx of zeta, is it not? Minus beta by only three terms. Only three terms. How do you get this? Suppose you have the what's the equation d by dt, the total derivative of f plus zeta, d by dt of f plus zeta equals to 0. What is this called? Conservation of absolute velocity. In this conservation of absolute velocity, is it not? Suppose you have, you write, is it not? This psi, the stream function, you all already know, probably knew these things in not intermediate, in your MSc course, is it not? So, partial derivative, is it not? Is you have, then del square psi, is the what's. Now you write, please write in your books, psi equals to psi cap. You all have Holton book, first be Holton book. Psi equals to psi cap into e to the power of ik into x minus ct. Psi equals to psi cap into e to the power of ik x minus ct. Is it not? Why psi cap? Anybody? Because psi cap is complex. Psi r plus I psi I. Okay? That C also can be complex. What is C? Phase speed. Is it not? Phase speed. What is e to the power of I theta? Please. E to the power of I theta. E to the power of I theta. Cos theta plus I sin theta. Is it not? Cos theta plus I sin theta. And now, and one more question. When I was teaching there in Brazil, one, what do you call, mischievous student asked, okay, e to the power of I theta is cos theta plus I sin theta. Cos is like this, and sine is like this, is it not? Sine is a typical wave. Why wave? Why not line? Why? We should treat only waves. Why not line? It's a legitimate question, is it not? Anyway, to convince this mischievous student, I brought a chart of 500 millibar. 500 millibar is polar stereograph projection. The center here, then the geopotential 500 millibar. How it looks like? Waves only, not lines. Is it not? The 500 millibar chart. So in reality, in nature, in the realistic nature, we have waves. And the middle latitude, typically, now we know, are Rossby waves. The first discovered. That's what I am trying to tell you. So, in real, if it is lines, we have to treat straight lines only. But we have to treat waves because we have waves. Also, patterns. There is what is called Fourier theorem. You all heard, is it not? There are what are called Dirichlet's conditions, generally valid. So generally, any function you can expand in waves. Any function you can expand to psi cos. So you have a legitimate, what you call, right or theory or whatever it is, to expand in waves. But in nature we have really waves only. We see that waves on the chart, is it not? So we treat waves. Because the natural question. Many people ask, why waves? Why not straight lines? Is it not? So we see waves, and if you want applicability, you put waves only. So here, now, another very probably many of you never heard. Please pay attention. Psi equals to psi cap into e to the power of e to the power of, what is the derivative of e to the power of x? E to the power of x only. So that's how normally people treat e to the power of x, e to the power of I, everything like that. Because e to the power of x, simple, same again the same derivative. It becomes very simple. Becomes the derivation, mathematics becomes simple. Because just like Professor Rosby, you know where you want to reach. I don't want complication. I want the simplest. But I want to reach the destination. That's exactly what I did. I don't want to teach spherical geometry. I don't want to treat spherical harmonics. I don't want to teach what you call legendary polynomials. And I don't want to teach sphere also. I want to teach on Cartesian geometry. So I used the beta plane. But he knew that's important. He had the perception that beta should be there because the so-called rotational Rossby wave, rotation will be there. Any planet, wherever there is planet, and that's why Professor Charney wrote that book, Planetary Fluid Dynamics. There are Rossby waves in Venus, there are Rossby waves in Mars, there are Rossby waves in Sun also. You know, there is one famous professor, famous VP Victor P. Starr, Victor Paul Starr. You know, he has a student, he studied for his PhD at MIT, where clinical instability, sun's atmosphere, sun also rotates. You know how much it takes, sun's rotation, anybody? Sun's rotation, 27 days, 27 Earth days, and 27 Earth days is the mean. At the equator it is less, at the a little higher it is higher. So in the equator, because less than 26, 25, rapidly rotate. That are, we have subtropical jets, is it not? So in the case of sun, equatorial jets. And in the case of earth, we have solid body and a gaseous envelope, thin gaseous envelope. Is it not? If you take Earth's diameter or from the center S radius, the depth of the atmosphere is very, very thin. That's why hydrostatic approximate is very, very valid. Because we have a thin atmosphere. All those who want to eat solid theory, I have papers if you want to read, I will give that difference also. So because of the thin gaseous envelope, hydrostatic approximate is very, very valid. Geostuff, you know, is valid only in the middle latitude. And the Rossby number is 1/10. Anyway, now that U, as I said, is constant. So there is no source. So the waves are neutral only. So that's why I put the title intentionally neutral Rossby waves. Now, psi equals to psi cap, e to the power of I k and x minus 3t. Psi cap is psi r plus I psi I. She is again CR plus ICI. CR is the real part, Ci is the imaginary part, and the waves move with the real part, and the waves grow with the imaginary part. Now another very, very important, please pay attention. I think we'll stop, it's becoming and now here. This type of approximation, putting psi equals to psi cap, mode approximation, normal mode. What is that?
Nothing.
Going the current.
Let.
So that is called, pay attention, normal mode. Putting psi equals to psi cap into e to the power of I k and x minus ct. This type of approximation is an approximation. It's called normal mode approximation. Means what? Normal mode means shape preserving. Shape it preserves. So you must have seen in Holton book, many of the analysis there is about this normal mode only. Recently, there is a research scholar or professor now, Brian Farrell, one of the students of Richard Lindzen. He showed very, very important. In nature, this doesn't exist. In nature, this type of normal mode doesn't happen. So, this type of analysis, normal mode, there the C, the phase speed, it comes as mathematically eigenvalue. It's called eigenvalue. Okay, so it is a eigenvalue problem. If you want to study instability, barotropic or baroclinic, this is the eigenvalue problem. Unfortunately, it doesn't happen in nature. You have shown that. What is written in the article, you have shown beyond doubt it doesn't exist in nature. So, what exists in nature? And how to go about it. This another approach is what's called initial value approach. Initial value approach. To solve the instability problem. Why instability? Because in nature, I know that there is tropical cyclone. It starts with a very, very weak, innocent low. Growth. Then it becomes category 3, 4, even 5. It grows. Wind increases. Wind increases means kinetic energy increases. Kinetic energy increases means it comes from somewhere it comes. The total energy is constant. Is it not? That means if the kinetic energy is growing means the amplitude is growing, or if you treat as a wave is unstable. D by dt of or dou by dou t of k greater than 0, unstable. Less than 0, stable. Equal to 0, neutral. So this is called an eigenvalue problem. In nature, this type of waves we have shown beyond doubt the so-called shape preserving. Okay, shape preserving normal mode doesn't exist. You have to part for initial value. We'll stop here. We will continue tomorrow.
Questions argument.
Yeah, anyway, if you have any doubts or questions, please.
Yeah, professor will be there. Very happy to.
You all got this? Yeah. These notes you all got?
Pakistan, Master. Huh? Pakistan. I'll share.
Please take a look at this. So simple. Now that I explained to you, I think you easily understand. Yes, sure. Just as Rossby's complicated spherical geometry, Legendre polynomial made simple. My talk always make simple to understand. Okay? Any doubt, please ask me. You know why I am shouting? You know, in Bhagavad Gita is what's called Purushottama Prapti Yoga. Purushottama Prapti Yoga. The first sloka, one of the gurus explained to me. The first sloka is Urdhamula Madasyaka Taswadham Pravaravayam Chandansi Yasyavarnani Yasam Veda Savedavid. That is the sloka. So he said, Guru said, whenever you start, this is the first sloka of that Purushottam. So whenever you start, you have to start Urdhvam. That's why I'm shouting at the top of my voice. All the and draining my energy. And then he said also in the class there are some naughty students. They say whenever they will wait, if there is anything wrong, the teacher is on. He doesn't know. He's saying something wrong. He says, Urdhva Moolam, roots are above, Athas Shaka. Shaka means branches are below. Then this fellow, what is this tree? Where it exists? It doesn't exist in nature. See? So purposefully, God incarnation, Krishna Paramatma, to catch the attention of whom? Partha. Prithvi means mud. So he is muddy-headed fellow. Partha, Prithvi Arjuna. Arjuna is called Partha, is it not? Arjuna is called Partha. The word Partha came from Prithvi, means earth, mud, is it not? So he is a muddy-headed fellow. So Lord Krishna, this is his interpretation anyway. It says, to convince him, he purposefully says something wrong. And today I did not say. What all I said completely correct. Okay.
Any doubts we have, we can spend some more time. There's also tea arranged in the other room. But sometimes the discussion is kept actually. How many of you work in this kind of direct field dynamics?
Any sort of doubt in meteorology,
You can ask.
professor will clear. Okay. And he can relate it to reality also. You have to realize in nature. So whatever.
Yeah, you people have 20 years only. I am 82. So I treated mesoscale meteorology. I love stratospheric dynamics. Stratospheric dynamics. Stratospheric warming. Some of these things. So you have anything? Of course, there are many things I don't know.
Yeah, I
cannot
forgot to
answer.
mention in his biodata, Professor Rao is the first quality A1 professor from the entire South American continent. Nobody has got that distinction. Maybe I think we should slate some more time for the students to interact.
Actually, there's an interaction at the
There
same.
in Brazil, they say, there's language Portuguese there.
No problem.
All my students say, tudo na cabeça dele. Everything is head. See, today I did not consult anything. Do not. Now, these things also I can do. Because I have been teaching for some decades now.
Yeah, don't think that he has given you something very basic and all. You can't catch up with his equations. For the last 20 years, I was not able to catch with his equations. Like, yeah, frankly speaking, yeah. There are many equations in his head. Yeah, purely theoretical. Yeah. He can make you realize what is baroclinic instability, what is barotropic instability.
But one thing very important for all of you, whatever you do, why to do it, and how to do it, where you want to do it. See, Professor Rosby, such a complicated, to give you an example of the complexity, there is Longate Higgins, a professor of fluid dynamics, a forest. He published a paper in President, he was a forest and all. Extremely complicated equations, Legendre polynomials, all those things. But something fantastic is what they reached finally, Professor Rosby also reached, it's much simpler, much easier, more relevant to us. Very simple. So you all also can do. But pay attention, you should pay attention to put a theory to it, not just description. Okay, matter long.
టీ అది అరేంజ్ చేస్తున్నారు
Huh?
టీ అరేంజ్ చేస్తున్నారంటే బయట
This